Welcome to Science to Sleep By. Wherever you are right now, whether you're resting after a long day, lying in a quiet room with the lights low, or simply seeking a moment of peaceful curiosity, I'm glad you're here. Tonight, we're going to drift gently into one of the most mysterious ideas in all of science. An idea so strange, so powerful, and so deep that it sits right at the edge of what the human mind can truly understand. We're going to explore the question, what is a singularity? Really? In everyday American life, we're surrounded by technology, comfort, and familiar routines, highways glowing at night, quiet suburbs under wide open skies, the steady hum of cities that never completely fall asleep. But far beyond our neighborhoods, beyond the atmosphere, beyond the farthest satellites drifting through space, the universe bends and curves in ways that challenge everything we think we know. In those distant places, the laws of physics begin to soften, stretch, and sometimes disappear altogether. And at the heart of that mystery lives the singularity. Tonight's journey is not rushed. There are no equations to solve, no pressure to understand everything at once. Instead, we'll move slowly, calmly, like floating through deep space itself. We'll explore black holes where gravity becomes infinite. We'll touch the future where artificial intelligence might one day surpass human thinking. And we'll stand at the boundary where time, space, and reality seem to fold inward. This is not a story of fear. This is a story of wonder, of silence, of vast distances and invisible forces quietly shaping the universe around us and within us. Let your breathing settle. Let the noise of the day fade into the background. And as your mind begins to unwind, allow curiosity to gently remain awake. Because tonight, we are not just asking what a singularity is in science. We are asking what it means for us, as observers, as thinkers, as small, quiet pieces of an enormous and mysterious cosmos, long before the word singularity carried the weight it holds today. Before it became linked to black holes, artificial intelligence, and the fate of reality itself. It began quietly, almost shyly, inside the minds of people who were simply trying to understand how the universe behaves when pushed to its limits. There was no dramatic announcement, no single moment when humanity suddenly realized it had stumbled upon one of the most haunting concepts in science. Instead, the idea formed slowly, across centuries, through observation, mathematics, and quiet curiosity. In the early days of science, the universe felt orderly in a comforting way. The skies moved in predictable patterns. The sun rose and set with steady rhythm. Planets traced their paths with elegant consistency. For people living in small towns, under wide American skies, or ancient European villages, the cosmos felt distant but dependable. Even when early astronomers discovered that Earth was not the center of everything, the universe still seemed like a grand machine that could, with enough effort, be understood. Then came gravity. When Isaac Newton described gravity in the 1600s, he gave humanity a powerful tool. Suddenly, the fall of an apple and the motion of the moon belonged to the same invisible force. The universe became something that could be written in equations. For over 200 years, Newton's laws gave scientists the confidence that nature, no matter how complex, always followed clear and predictable rules. The universe was a clock. Every gear had its place, but even in that era of certainty, tiny cracks already existed. By the early 1900s, a quiet revolution began. Albert Einstein introduced the world to a new way of thinking about gravity, not as a force pulling across space, but as the bending of space and time themselves. His theory of general relativity suggested that massive objects warped the fabric of the universe, and that motion followed those curves. At first, these ideas seemed abstract, even poetic. Space could stretch, time could slow. The universe was no longer a rigid framework. It was elastic. As scientists explored Einstein's equations more deeply, they discovered something strange hidden inside the math. When matter collapses into a small enough region, the curvature of spacetime becomes infinitely steep. The numbers explode. Density becomes infinite. Gravity becomes infinite. At those points, the equations break. The laws stop making sense. These strange breakdowns were given a name: singular. At first, singularities were treated almost like mathematical ghosts. They appeared on paper, but many physicists believed they were not physically real. Nature, after all, was thought to be well behaved. Surely the universe would not allow true infinities to exist. Infinities felt like mistakes, like warning signs that the math had gone too far, but the equations refused to let go of the idea. In 1916, Carl Schwarzschild found an exact solution to Einstein's equations that described what happens around a perfectly spherical mass. Hidden in that solution was a point where gravity became so intense that not even light could escape. At the center of this object was a singularity. At first, this too was seen as a curiosity, not a real thing that could exist in the universe. But as decades passed, and evidence for collapsed stars mounted, black holes moved from theoretical oddities to accepted cosmic objects. And at the heart of every black hole, according to the math, was a singularity. Quietly, the universe had revealed a place where its own rules fell apart. Meanwhile, a different kind of singularity was beginning to take shape in another corner of human thought. This one had nothing to do with gravity or space, but with progress and intelligence. In the middle of the 20th century, as computers grew from room-sized machines into increasingly powerful thinking tools, a few forward-looking scientists began to wonder what would happen if machines became capable of improving themselves. One of the earliest to hint at this idea was John von Neumann, a mathematician who noticed that technological progress seemed to be accelerating. Each invention led more quickly to the next. It makes up more than a quarter of the universe's mass energy content, yet it does not emit or absorb light, making it invisible except for its gravitational effects. Some scientists have proposed that tiny black holes could account for part or all of dark matter. If a population of primordial black holes formed in the early universe, they could be drifting through galaxies, including our own Milky Way, influencing stars and gas through their gravity while remaining undetectable by ordinary telescopes. This idea has inspired numerous studies seeking signs of their presence, such as gravitational microlensing events where a passing black hole slightly magnifies the light from a distant star. These searches have constrained the possible abundance of certain sizes of primordial black holes, but they have not ruled out all possibilities. The idea remains intriguing, especially because it ties together cosmology, particle physics, and gravitational theory in a single elegant framework. Tiny black holes also challenge our understanding of physics on a fundamental level. If they exist, they could provide clues about how gravity behaves when pushed to the extremes of density and scale. They might help unify general relativity and quantum mechanics, two pillars of physics that currently resist complete integration. The mathematics describing their formation, structure, and evolution forces scientists to confront the limitations of current theories and search for new principles governing the universe. Even if no tiny black holes are ever discovered, the theories surrounding them continue to inspire research, experimentation, and debate across the scientific community. Their very possibility pushes the boundaries of what we know about the cosmos and encourages us to imagine how much more there is yet to uncover. When scientists explore the idea that primordial black holes might surround us, they are stepping into one of the most fascinating and quietly profound possibilities in cosmology. Primordial black holes, unlike black holes formed from collapsing stars, would have emerged in the earliest instance after the Big Bang, long before galaxies, planets, or even atoms existed. To understand the magnitude of this idea, imagine the universe as it existed at less than a trillionth of a second old, a seething ocean of energy and quantum fluctuations, where regions of space differed ever so slightly in density and temperature. These tiny imperfections, magnified by the rapid expansion known as cosmic inflation, could have created pockets where matter and energy were compressed to such a degree that they collapsed under their own gravity, forming black holes of all possible sizes, from microscopic scales to many times the mass of our Sun. The smaller ones, the ones scientists theorize might still be drifting quietly through galaxies today. are the very objects that raise the possibility that we may be surrounded by them without ever noticing their presence. The key idea behind primordial black holes is that they originated before the formation of stars, meaning they are not limited by the physics of stellar evolution. A star must reach a certain mass to collapse into a black hole, but primordial black holes were shaped by conditions in the early universe where energy densities alone controlled their formation. This means their potential masses could span an enormous range. Some could be as small as an asteroid, others as tiny as subatomic particles, with masses comparable to mountains confined to microscopic radii. This range of possibilities makes primordial black holes one of the most flexible theoretical candidates for dark matter, the mysterious material that makes up about 27% of the universe's mass energy content. The reason scientists believe primordial black holes could be all around us is tied directly to their gravitational behavior. Dark matter does not emit, reflect, or absorb light. We only know it exists because its gravity affects visible matter. If primordial black holes formed in large enough numbers billions of years ago, they could now be scattered throughout galactic halos, including the one that surrounds our own Milky Way. They would not shine. They would not distort space in obvious ways unless one passed extremely close to us. And they would not interact with atoms through electromagnetic forces. Their presence would be ghost-like, detectable only through the gentlest gravitational tug or through rare events where they briefly magnify the light of distant stars as they drift between us and a background source. This possibility becomes even more compelling when we consider the observed distribution of matter in the universe. Astronomers have spent decades attempting to identify what dark matter consists of. They have searched for exotic particles like WIMPs, axions, and sterile neutrinos, each representing hypothetical forms of matter that may fill the cosmos. But none have been conclusively detected, despite large, highly sensitive experiments running deep underground and in space. At the same time, studies of the early universe and galaxy formation have revealed clues that seem to leave room for primordial black holes of certain masses. They cannot be too numerous at certain sizes, or they would produce effects astronomers would already have observed. They cannot be too scarce if they are to account for dark matter. The narrow mass ranges that remain possible form a kind of scientific sweet spot that continues to attract interest. One of the most intriguing reasons for renewed interest in primordial black holes comes from modern gravitational wave observations. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time, a discovery that confirmed a major prediction of Einstein's general relativity. Since then, LIGO and Virgo have detected dozens of black hole mergers. Some of these black holes are about 30 times the mass of the Sun, a size somewhat unusual for black holes formed from dead stars. A number of physicists propose that these merging black holes might be primordial in origin, especially because they formed pairs early in cosmic history and drifted for billions of years before merging and sending out ripples in spacetime. While later studies offered alternative explanations rooted in stellar evolution, the possibility that some small fraction of these mergers involve primordial black holes has kept the idea alive and highlighted how little we truly know about the full population of black holes in the universe. To imagine whether primordial black holes could be near us, consider how vast space is and how rarely small objects interact. Earth orbits the Sun at about 93 million miles away, yet space between planets is effectively a vacuum. If primordial black holes exist as part of dark matter, they would be dispersed extremely sparsely, perhaps with densities of one tiny black hole per several astronomical units, or even more. Even if one passed through the solar system, it might never come close enough to Earth to produce noticeable effects. And even in the unlikely event that one did cross the path of our planet, its interaction with matter would be minimal, unless it were unusually massive. A primordial black hole with the mass of a large mountain, but the size of a subatomic particle would pass straight through Earth almost unnoticed, interacting so weakly with atoms that most matter would simply flow around it the way water flows around a Small stone dropped into a deep river. Another reason primordial black holes could go unnoticed is their temperature and radiation output. According to Hawking radiation theory, black holes lose mass over time by emitting energy. The smaller the black hole, the faster this process occurs. Those with extremely small masses would have evaporated long ago in bursts of high-energy radiation. However, primordial black holes above a certain mass threshold would evaporate so slowly that the process would effectively be invisible on human timescales. These black holes would be cold, dark, and silent, with no glowing accretion disks or jets of radiation like the ones observed in large black holes at galactic centers. Their presence would be nearly impossible to detect unless an extremely lucky astronomical alignment occurred. Observational surveys have attempted to find signs of these objects through gravitational microlensing, where a massive but invisible object drifts in front of a distant star and slightly magnifies its brightness for a short period. These experiments, conducted from observatories around the world and space-based telescopes, have narrowed the possibilities for primordial black hole masses, but have not eliminated them entirely. Some mass ranges remain viable, and those ranges correspond to objects small enough and sparse enough that they could fill halos of galaxies. Without creating observational contradictions, the idea that primordial black holes might surround us is not meant to provoke fear, but curiosity. Their gravitational effects would be so subtle that Earth would continue moving through the galaxy exactly as it always has. The solar system would remain stable, the Milky Way would remain structured, and life would continue without interruption or danger. In this view, primordial black holes become quiet cosmic passengers, drifting through space as relics of the universe's earliest moments. Their existence would provide a direct connection to the extreme physics of the Big Bang, carrying within them information about conditions we cannot otherwise observe. For scientists, the possibility that these ancient, tiny objects could be all around us adds a serene layer of mystery to the cosmos. It suggests that the universe is filled not only with stars, galaxies, and bright cosmic structures, but also with silent, hidden remnants of creation itself, drifting through the darkness as unnoticed witnesses to the entire history of space and time. When people first hear the idea that tiny black holes might be drifting through our galaxy, or even passing near our solar system, the instinctive reaction is often one of concern. Black holes, after all, carry an almost mythic reputation as cosmic vacuum cleaners, devouring everything around them. But the reality of how gravity works, especially on very small scales, paints a very different, much calmer picture. The laws of physics tell us that even if primordial or microscopic black holes fill parts of the universe, their presence would be almost completely undetectable because of how weakly they interact with matter, how minuscule their gravitational influence becomes at even modest distances, and how quickly many of them would evaporate through Hawking radiation. Understanding why we would not notice them requires stepping back from popular imagination and grounding ourselves firmly in the scientific principles that describe gravity, quantum behavior, and spacetime. The first important thing to understand is how gravity scales with distance and mass. When we think of black holes, we tend to picture massive ones, objects with the mass of stars or entire clusters compressed into a small region. Those black holes have event horizons spanning kilometers or even billions of miles. Their gravitational pull is significant because their mass is enormous. A tiny black hole, however, could have the mass of a mountain confined to a radius smaller than a proton. The event horizon of such a black hole would be extraordinarily small, first smaller than anything visible or physically interactive at human scales. At very short distances, such an object would exert an intense gravitational pull, but the effect drops off rapidly as the distance increases. Just a few millimeters or centimeters away, the gravitational influence of such a black hole would be far weaker than that of Earth, your desk, or even a cup of water sitting next to you. This means that unless a tiny black hole were to pass directly through an object, it would exert practically no noticeable gravitational effect at all. simply because of how small its radius is and how fast gravity weakens with distance. The second reason tiny black holes would go unnoticed is that they do not behave like cosmic vacuum pumps. They do not actively seek out matter to consume. To pull something in, that thing needs to cross the event horizon, which, in the case of a microscopic black hole, is so unimaginably tiny that atoms and even atomic nuclei are far larger than the region the black hole can interact with. Matter on the scale of atoms and molecules is mostly empty space, and as a tiny black hole moves through matter, it would pass between atomic nuclei rather than collide with them. The probability of it capturing even a single nucleus is extremely small. A black hole the size of a subatomic particle might pass through the Earth without capturing more than a few particles, losing almost no speed and leaving the planet unaffected. This is why physicists describe black holes not as cosmic vacuum cleaners, but as objects that simply follow whatever gravitational path they are already on, interacting with matter only when chance puts something directly on their event horizon. Another factor making tiny black holes nearly impossible to detect is their dark, silent nature. Large black holes emit signals because of the environment around them. Gas spiraling into them heats up and glows brightly, creating X-rays and other radiation. Jets and accretion disks form when matter is being consumed, and these structures emit energy detectable across millions of light years. Tiny black holes lack the gravitational reach to pull in enough matter to produce these luminous effects. A microscopic black hole drifting through space would not form an accretion disk. It would not collect gas or dust. It would not emit light, X-rays, or radiation triggered by infalling matter. It would simply be dark, cold, and moving quietly through the vacuum without disturbing anything around it. Hawking radiation adds another layer to this quiet invisibility. According to theoretical predictions, black holes emit radiation due to quantum effects at their event horizons. The smaller the black hole, the higher the rate of evaporation. Those with extremely small masses, perhaps the size of an atom or smaller, would evaporate extremely quickly, disappearing long before they could interact with any object in a meaningful way. They would release a brief burst of particles and energy, but such an event would need to occur close to Earth and be detected at the right moment to be observed. The vastness of space means that even if millions of tiny black holes formed in the early universe, the chances of observing the evaporation of one are extraordinarily small. Larger primordial black holes that might still exist today would evaporate so slowly that their Hawking radiation would be weaker than the cosmic microwave background, effectively rendering them invisible to current instruments. The inability to detect tiny black holes also stems from the sensitivity limits of our observational tools. Telescopes detect light, radio waves, infrared emissions, X-rays, and gamma rays. They detect massive gravitational distortions through lensing. For a tiny black hole to bend or magnify light from a background star, it would need to pass directly in front of that star from our line of sight. An alignment so precise and rare that years of continuous monitoring are required just to find a handful of potential candidates. As we come to rest at the far edge of this quiet journey, the idea of the singularity no longer feels like a sharp question demanding an urgent answer. Instead, it settles into the mind as a gentle reminder of how vast and layered reality truly is. From the silent birth of the concept in patient equations, to the hidden hearts of black holes, to the rising tide of machine intelligence, to the fragile bending of time and gravity, and finally, to the uncertain future of humanity itself. The singularity has revealed itself, not as a single object or moment, but as a boundary that appears wherever understanding begins to thin. What we have touched tonight is not fear, and not certainty, but scale. The scale of a universe that allows stars to collapse into points beyond description. The scale of intelligence that may one day outrun its creators. The scale of time that can slow, stretch, and possibly dissolve at the deepest edges of gravity. Each version of the singularity points to the same quiet truth, that reality is larger than the stories we use to describe it, and yet, within that immensity, the human experience remains intimate and steady. Breath still rises and falls. Hearts still keep their quiet rhythm. Lives still unfold in ordinary rooms, under familiar skies, within the warmth of connection and memory. The singularity does not pull us away from these things. It simply places them within a much deeper and more mysterious frame. We are a species that learn to look up, to ask why the stars move, why time passes, why intelligence awakens. The singularity is the continuation of that ancient questioning, carried to its most distant horizon. It reminds us that knowledge is not a closed circle, but an ever-widening shoreline where solid ground slowly fades into deeper water. We walk as far as we can, and then we listen. There is something quietly beautiful in knowing that the universe still holds places where our language grows soft and uncertain. It means there is still room for wonder, still room for humility, still room for discovery that does not arrive as conquest, but as invitation. So tonight, as thoughts slow and the edge of sleep draws near, you do not need to solve the singularity. You do not need to define it or tame it. It is enough to simply know that somewhere, far beyond the reach of light, time, or prediction, the universe keeps a few of its deepest secrets close to itself. And here, within the gentle gravity of rest, you are free to let those secrets remain what they have always been: quiet companions to curiosity, drifting just beyond the horizon of understanding as consciousness softens and the long questions of the cosmos fade into the peaceful dark, where wonder and rest become indistinguishable.